Let's discuss chain reactions. Reactions involving free radicals and atoms often follow chain reaction mechanisms. These reactions are important in combustion. An example that we're going to show here is going to be the gas phase reaction of H2 plus Br2 to give you hydrogen bromide, HBr. This is initiated by collisional activation of the Br2. The first step involves collision of Br2 with a third body. That's an initiation step. Initiation is a reaction that increases the number of radicals. In this case, the number of radicals is going up by 2. The second and third steps are chain propagation steps. These conserve the number of radicals while producing a product, HBr in this case. Step 4 is an inhibition step. It consumes our product and reproduces one of the reactants. Finally, there's a termination step that reduces the number of radicals. Following initiation, chain propagation steps can occur many times before inhibition or termination steps occur. Let's take a look at the early reactions. That is, when the initial concentration of H atoms is low and inhibition can be ignored. Let's write down an expression for the rate of change of the HBr product as a function of time. We add up the two steps that create HBr, and we identify bromine atoms and hydrogen atoms as intermediates. Now we can apply the steady state approximation and remove these two concentrations from the rate expression. We write down first a rate expression for differential rate law for the H atom concentration and another for the bromine concentration, adding in the steps that create bromine, subtracting out those that remove bromine from the system. At steady state, intermediate concentrations are constant, so we set these two terms equal to 0. If we add these two equations together, we can solve to get an equation for the bromine concentration at steady state. Similarly, we can go back to the differential rate equation for H plus and solve for the hydrogen atom concentration at steady state. We'll now substitute these two expressions in for the atom concentration, which gives us the final differential rate law for the hydrogen bromine concentration and how it changes with respect to time. And what we see is that we get a rate constant times the bromine concentration raised to the 1/2 power and its first order in H2 concentration. Partial orders, fractional partial orders like 1/2 and 3/2 are typical for chain reactions in addition to the more usual first and second order terms. Now, if we go to later, longer times, then we can't ignore inhibition. If we can't ignore inhibition, that's going to change the kinetics. And it's a much more involved mathematical process if we have to derive the rate law. I'll spare you those details, but we'll just compare the kinetics at early times and the kinetics at late times when we have to include inhibition. And sure enough, with that inhibition step, we see that the concentration of the product, HBr, appears in the denominator. So as the concentration of HBr increases, the rate of production of HBr goes down. HBr is acting as an inhibitor. An inhibitor decreases the rate. In this case, it's one of the products that's acting as an inhibitor. In other cases, and in general, it turns out that chain reactions are very sensitive to additives or impurities that might be in the system. Some molecules produce stable radicals, some molecules like oxygen and organic radicals that include phenyl groups. They have very stable molecular radicals, and these can slow down reactions. They act as inhibitors. Other species, other additives, act as initiators. They increase the rate of reaction. But an initiator isn't a true catalyst because it's not regenerated during the reaction.